Okay, let's learn about vectors and delta notation. Okay, I hope I spelt that right. Vectors and delta notation. Okay. Um, all right. So first things first, the the area that we're about to start studying here is it's called kinematics. Don't let that word scare you, but kin has the same root as kinetic, and that refers to something that's moving. So essentially, kinematics is the study of objects that are moving. Okay. Um, it's really nothing more than that. And the good thing about what we're going to do is essentially we're only going to study objects moving in 2 dimensions. So for us, kinematics will only involve 2D motion, 2-dimensional motion. So what are the 2 dimensions? Well, basically they're right and left, or up and down. Okay? So that's it. We're going to talk about objects that move in one of these two ways. All right? And before we get into vectors and delta notation, we need to do a little bit of miniature review. Okay? And this starts, I think, really quite easy. And if you keep on top of it, it will continue to be easy. But as I said before, if you allow yourself to get behind, that's where the problems may start. So we're going to review the number line. Okay? So a number line is just a line, and onto this line we put evenly spaced intervals, and we mark them. So 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, so on. And if we go the other way, 2, 3, 4, 5, we might say this is into negative numbers over here. So, is everyone okay with this so far? The number line. Yeah, so far so good? This is taking you way back to elementary school. So, when we're studying motion, these intervals are going to represent something, okay? And generally what they're going to represent is units of distance. So the main unit of distance that we're going to use is the meter. So this number line, as I have it drawn, represents, you know, some place in the world. We'll call it the origin. Okay. And usually the origin is the place where an observer is standing and watching, right? So here's an observer. And that observer could be you. Here's you with your little baseball cap, you know, just watching what's happening over here on the number line. Okay? Are you with me so far? So if an object were to move on the number line, okay, if they move in this direction, or to the right, based on where the observer is standing, okay, so here's to the right, we can see that this object is moving in the positive direction. Does that make sense? It's moving towards higher positive numbers. So far, so good? So let's imagine that you're watching, I don't know, like a little bunny rabbit. And the bunny is, you know, hop, hop, hopping along, okay? We would say that that bunny is moving positively, okay? And if the bunny were to hop, hop, hop in the opposite direction, how do you think we would say the bunny is moving? Yeah, excellent, negatively, so left. Okay, so this is positive motion, and this is negative motion. Now, positive and negative here really are only talking about direction. Does that make sense? Okay. So let's write down a few things in terms of in terms of the proper, I guess, terminology for this unit. So this is kind of the thinking behind what's going on here. And what we're really talking about are vector values, okay? So vector values, we'll define what they are, and then we'll talk about how what we just looked at is an example of vector values. So vector values are measurements with both magnitude. What do you think magnitude means? What's the magnitude of something? What's another word for magnitude? Starts with S and ends in I's. Right, size. And when we say magnitude, it means a size numerically, like a size with numbers. So if I said if I went 10 meters, well, the magnitude of how far I went, the magnitude of the distance is 10 meters. So that's what magnitude means. Okay, so measurements with magnitude and direction. Okay, so it's got to have magnitude and direction. Okay, so let's talk about how that applies to the bunny. Okay, so over here, if we say the bunny hops 5 to the right, okay, so let's write that down. 5 right. Okay, well, what we've done is we've actually written a vector value down. Okay, so it is a distance in a way, because we know that there's a 5 there, but distance doesn't include direction usually, right? Okay, so 5 right is considered a vector value, okay, because it has a direction and it has a magnitude. So we're going to write down some things that are vector values, and then we're going to come back and look at this, and we're going to talk about the difference between that and scalar values. So first of all, vector values. So one vector value is displacement, okay? And what displacement is essentially like distance with direction. Distance with direction. So when I say the bunny moves 5 right, I'm telling you it's displacement. Okay? Are you with me so far? So far, so good? Okay. Another one is velocity. And this is like speed with direction. You know, if you're driving along in your car and you're driving at 100 kilometers per hour, that's the speed. If someone outside is watching you and says, you're going 100 kilometers per hour to the right, that's velocity. And one more one that we're going to study in kinematics, right, because these have to do with motion, right, is acceleration. And this is essentially a changing speed with direction. Okay, so I'm going to go back up to the bunny scenario. Okay, let's go back to the bunny. Okay, so actually we'll just bring the number line down and work with it here. All right, so let's figure some things out. Okay. Oh, and one more important idea in this unit is the concept of position. Okay, so position is the current location of the object based off the origin. Okay, so let's talk about the bunny. Let's say that the bunny starts over here. Okay, so the bunny's position at the beginning, and seeing as how we judge where something happens based on time, right? Something that happened before now happened in the past, and something that happens after now is in the future. But what I just said is now in the past. We can say that this is T1. So we'll call it time 1. Does that make sense? To call this time 1? It's the first place that the bunny is. And then what's going to happen is the bunny is going to hop, 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 hop over here. And I think I should draw the bunny because I like to draw bunnies. Be a little bit different than the last bunny because I'm not a very good artist. Okay, and let's say the bunny ends up here at T2, at time 2. Okay, so the bunny has hopped over to here. So position at T1 or initial position, is equal to negative 1, oh sorry, 5, 6, 7, 8. Negative 8, and we said this unit was in meters, so negative 8 meters. So the bunny's position when we start is negative 8 meters. Are you with me so far? Simple, right? Makes sense. And then at time 2, sometime later, the bunny is now over here at position 1, 2, 3. 3 meters. You can draw the plus in here, but it's convention to not bother. Like if I just write this number, you know it's positive 4 without me putting positive, so it's usually unnecessary to put the positive in. However, since we don't as commonly deal with negative numbers, you have to say when it's a negative number. Okay, so now the big question. How far did the bunny move? And did it move positively or negatively? And you know what? While we're at it, just while you're thinking about that, let's call this P1 for position 1 and this P2 for position 2. Okay? And you might see it as P, and sometimes you might see it as D. Doesn't really matter. You know what it means. So how far did the bunny move? Well, it moved 8 to get here, didn't it? So plus 8. 1, 2, 3, 4, 5, 6, 7, 8. And then it went 3 more. 9, 10, 11. The bunny moved 11 to the right. So what we would say is we would say displacement of the bunny is equal to 8. No, that's not right. 8 meters plus 3 meters. Don't worry, I'll show you a shortcut in a second. 11 meters total. Positive 11 meters. Okay? So far, so good. Are you with me? All right. Now, it would be a giant pain to have to draw out a number line every time you wanted to do math with this. So we're going to rely on your abilities with algebra to write this in a little more of a simple way. Okay? So what we'll say is we'll write it in words first, and then we'll write it in its equivalent with math. Okay? So we'll say the change in position must be equal to the difference between position 2 and position 1. Okay? So how far the bunny went is the difference between where it was and where it is now. Okay? So what does difference mean in mathematics? How would I express something that's a difference? What is the difference between 8 and 3, for instance? Or 15 and 5? What's the difference between them? It's 10, right? So what did I do? I took 15 and I subtracted 5 away and I got 10, right? You guys use the term difference still these days, don't you? No, you don't? Oh. Okay, well, it's a pretty common math term to use difference if you're talking about, you know, the difference between two numbers, because that's essentially what it is. You might say subtract, but what you mean is difference between, right? So how do we write this in physics language, in math language? So in math language, instead of saying the difference between, we say delta P. Or sometimes you might see people write it like that, but that's for later. Okay, for us, we're actually going to draw a triangle. This symbol is delta. Have you heard of the symbol delta before? Yeah? It's the Greek letter delta. If you ever forget, if you think of like geography, a delta is like where the end of a river happens and it spreads out into a large triangle shape. That sometimes helps me think about it. But delta P, that means difference between the two numbers. So delta P equals position 2 minus position 1. Okay? So what this says, in a very concise way, using just symbols, is the difference between the final position and the initial position is the change in displacement, or the change in position. Okay? So we'll rewrite it just in terms of displacement. We'll say delta D equals P2 minus P1. And let's see if it actually works out. Okay? So delta D in this case is going to be P2. Now P2 was 3 minus subtract, right, -8. These are both meters. So let's put our brackets in. And what is 3 minus -8? Well, it's the same thing as 3 plus 8, right? Two negatives side by side. 3 minus -8 is the same as 3 plus 8, and look at that, we get 11 meters. The displacement of the bunny is 11 meters, and it's positive. Pause there first. Okay, now I'm going to get you guys to try one on your own, okay? And then we'll talk a little bit more about what I want you to do for your homework. Oh, I changed its color. That's cool. Nice one. Okay, I'm learning all kinds of new tricks I can do on here. Okay, so let's try the bunny again. And we'll say now, the bunny starts at, I don't know, 7 meters. So here, there's its initial position. And ends up at -10 meters. So it ends up over here. So that's position 2. So what do I want you guys to do? I want you to find the displacement of the bunny. And you can count it, but I also want you to write it out in terms of delta notation. So delta notation, again, reminding you, delta D, the change in displacement, is final position minus initial position. So I'll give you a second to give that a try. So writing this down, okay, what we're looking for, and so something to consider here, right, just about displacement, is that knowing the displacement itself tells you the difference in position, but it doesn't tell you where that actually happened. So for example, if we look at here, so we have -10 minus 7. Well, -10 minus 7 should work out to be -17. Okay, so the bunny moved -17 meters. Unless we know that it started here, we have no idea where it ends up. If I just say the displacement of the bunny is -17 meters, you might think it started at the origin, and then it would be at -17 meters right now. Okay, so you need more information than just displacement to know where it actually went. How many people got -17 for this? Right on, you're already experts. Okay, so we learned a lot, and I'll just do a quick recap, because we actually surprisingly covered quite a bit of stuff in a very short amount of time. So recap, number 1, vectors. Well, these are measurements with magnitude and direction. Okay, now when we say direction, we know in real life it's left and right, but you can't do math with left and right, can you? Not really, right? So the way we do that is we make negative and positive stand in for left and right. Then we can do math with it, right? Math understands negative and positive, but it doesn't understand left and right. So the direction is indicated by plus and minus. Okay? So lots of times people are like, well, how can you have a negative displacement? How can you have a negative velocity? Easy, right? I have a negative displacement here because I'm moving left on a number line. It's just that simple. If I time it, then I could figure out the velocity. Like if I knew how long this took, like let's say it took 17 seconds. Well, then I know it's moving 1 meter every second to the left. It has a -1 meter per second velocity. If you think about it in terms of a number line, that makes sense. Could you ever have a negative speed, though? Does speed make sense in terms of negative? Not really. You can't say, hey, I was driving my car like -80 kilometers per hour last night. People just look at you like you're crazy. So that is one other difference, right? Vectors can be negative, and the negative indicates the direction, okay? Scalar values, which we'll just, before we're done, mention, can't have negative values. Okay, so vectors, magnitude and direction. Direction is indicated by plus and minus, and the two vectors that we've experimented with are position, so that's where on the number line the object is, with respect to the origin, and displacement, which is essentially how much position has changed. Okay, so the change in position is called displacement. The other thing we talked about was delta notation. And delta notation is just a way to talk about the difference between two measurements in a very easy way. So the generic way of doing it is delta x, whatever x happens to be, whether it's position, velocity, displacement, whatever, change in x or delta x is equal to the final position or final measurement minus the initial measurement. And there you go. That's delta notation. Okay, and one last thing before we're done, scalar values. Well, these have magnitude only and no direction. And you're very used to using them because they're things like speed, distance, and if you want to extend this into other areas of physics, mass, okay, etc. So things where it doesn't make sense to have a plus or minus or a direction attached. Are there any questions?